Welcome to Pathways in Computer Science. We are joined today with Dr. Nathan Bronson. I am so excited for you all to be able to learn from him and to hear about his pathway in STEM. This is going to be a very exciting presentation. So first, before we get into our presentation, we're going to go over CEE for any of our new friends that are just popping in to figure out what Lyceum's all about. So, the Center for Excellence in Education was founded in 1983 by Joanne DeGennaro and the late Admiral H.D. Rickover, who is the father of the nuclear navy and civilian uses of nuclear power. Our mission here at CEE is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics, or STEM, and to encourage international collaboration between and among leaders in the global community. At CEE, we have 4 programs, the first of which is RSI, the Research Science Institute. RSI is a highly competitive 6-week summer science and engineering program open to rising high school seniors. Juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. We also have the U.S. Biolympiad, or USABO. USABO is the premier U.S. biology education and testing program for high school students. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Biolympiad team has medaled at the IBO. Next, we have the Teacher Enrichment Program. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. Finally, we have STEM Lyceums, the club that you are in right now. STEM Lyceums is a virtual club for high school students to meet twice a month to learn about STEM career pathways from leading field experts. Industry professionals share cutting-edge research and offer unique learning experiences like scholarships and internship opportunities for high-achieving students. All right, so now I get the opportunity to introduce our speaker for today, Dr. Nathan Bronson. Nathan Bronson is a software engineer at OpenAI with a diverse career spanning academia and industry. After attending RSI in 1991, Nathan took an unconventional academic path, completing his undergraduate studies at Duke in 1998 on his 3rd attempt, before eventually earning a PhD in computer science from Stanford in 2011. His professional experience ranges from small startups to large tech companies, including a decade at Facebook. Nathan remains actively engaged in academia, intermittently publishing research and regularly serving on program committees for conferences in systems and networking. He currently lives in Cambridge, Massachusetts. Nathan will share his experience with imposter syndrome, reflect on how a PhD fits into a software engineering career, discuss insights he gained from key decisions along his journey, and give candid answers to your questions. Please, please, please submit your questions as we go along in the presentation. I will be sorting them through them as we go along, and we'll moderate the conversation at the end of the presentation. So Q&A, anytime you have a question, just drop it in and I'll make sure that we get to it. All right, I'm going to pass it on over to Dr. Bronson. Thank you so much for joining us.
Thank you. I will endeavor to say as few times as you did, which is pretty amazing. My name is Nathan Bronson. I'm not usually Dr. Bronson, mainly when people are trying to solicit donations from me, but I went to RSI in 1991, which is how I'm associated with CEE. So that had a pretty big positive effect on my life trajectory. First, I want to talk a little bit about what I think, like, why do I love computer science? Why do I think it's a great thing to be a part of? For me personally, I love the fact that it gives very high leverage. So what I mean here is that if I write a computer program and that computer program is running on hundreds of thousands of computers or a million computers, like even small changes in what I do actually have kind of like a big change in the outcome of how it affects other people. Like there's an opportunity, like if I can make something a little bit better, but there's millions or even hundreds of millions of people using it, that the small kind of multiplies by a large, and then you actually end up with a big effect. If I save 10 milliseconds of time for a million people, that's like a day of life saved. Actually, sorry, Yeah, that's right. No, 100 milliseconds of time. 100 milliseconds of time on a million people is about a day of humanity. Computer science has an opportunity for continual learning. In fact, kind of a requirement for continual learning. The field has been rapidly evolving. Uh, so if you are somebody that likes learning in addition to just only doing, it's a good place to be. And it's also kind of a creative endeavor. Like uh, typically, you don't end up having to do exactly the same thing twice because if you are doing it again, you just reuse the code you have from before. Although it does have some challenges, probably in common with pretty much any kind of deep intellectual work. It can be hard to turn it off at night. Like if you're thinking about something during the day, like your brain just doesn't just stop thinking about it when it's time to go home and have dinner with your family. And especially in the modern world, people don't necessarily like write a piece of software and then ship it. Like you're constantly refining it. Maybe you're actually running the software instead of shipping the software. So there's never this like clear moment of like being done. So you kind of have to constantly make trade-offs between deriving value from something by using it and trying to make it better. And nothing can ever be perfect. Maybe that's only a trouble if you're a perfectionist, but uh, and then there can be parts of computer science work that are a little bit boring. So like writing your tests, or maybe there's a piece of glue code that isn't really intellectually stimulating. When I was younger, I used to have I called it the doldrums. So the doldrums is a place in the ocean where there's not really any wind. And back when ships were sailing ships, if they accidentally sailed into the doldrums, then they got stuck, and then they would end up waiting there for a couple of weeks until the wind would pick up and let them continue sailing. So it was kind of a sailor's nightmare. So I used to get stuck in the doldrums. Like I would procrastinate doing the thing I didn't want to do, but that would mean I didn't finish it, and then I would be kind of stuck there for a week or so, even though it would only take a few hours to accomplish. So I want to tell you how I started doing computer programming. When I was in ninth grade in 1988, I think. For various reasons, I spent a year living in Africa, in the country of Togo. Togo is pretty near the equator, so it's actually a pretty hot place. It just happened to be that there was this kind of confluence of events that allowed there to be a computer and a computer room that was air conditioned. It was the only air conditioned room that I had access to, and a copy of Turbo Pascal and a Mastering Turbo Pascal 4.0 book by Tom Swan. And there were also some Byte magazines. And so I basically I retreated to the computer room because it was air conditioned, and then I started programming because it was fun, and I didn't really have anything else to do because I didn't speak French. And so I just coded and taught myself to code. And there was a magazine article there that had an article about fractals, not the like Mandelbrot style things, but the kind of recursive decomposition ones, like the Sierpinski gasket or whatever. And I just thought that was the most amazing thing in the world. So I basically spent the summer learning to program so that I could make my own fractals. I'm a big fan I mean, it's valuable to go through material like here's a course. These are all the things you need to learn in order to make sure you don't have any gaps. Um, but I think there's also a lot of value in actually just I want to make this thing work, and therefore I'm gonna like it's kind of like a project driven thing. So you might maybe you learn maybe you skip maybe you miss some of the breadth of algorithms or whatever, but actually see something that you enjoy come to life. The 1988 was a long time ago, so like a lot of things have changed. So like how do you translate? I looked up some of the stats on the computer that I started on versus so I've got an iPhone 16 Pro in my pocket. So this phone has more than 10,000 times as much RAM. It's way more than 10,000 times as fast in terms of like its processing power. Uh, the flash drive in the phone is more than 10,000 times bigger than the hard drive on that computer. That computer has a 10 megabyte hard drive. So like 10 megabytes is kind of like that's like a photo attachment or something like that nowadays. It's not something we think of as being the whole thing. The only thing it doesn't have 10,000 times more of is pixels. There's only 14 times as many pixels on my phone than there are on that computer. But so how do you even translate something across that many orders of magnitude? There was also no internet at the time. I think 1988 was the year that the second country got attached to the internet. So the internet did exist, but it was not in Togo, and I had not encountered it yet. Um, I describe myself often as a systems programmer. So I want to tell you what that means. So if you have a computer program that computes something, we can do some sort of algorithmic analysis to try to figure out like how well does this algorithm scale? Like if I double the size of the problem, does it take 4 times longer, 2 times longer, maybe like less, more. For example, sorting, if you take like n times the logarithm of n, that gives you the kind of the scaling of how long it'll take to sort n things if you have a good sorting algorithm. So if you make something twice as big, it takes a factor of 2 from the n plus also the log n part. The constant factors are when you translate the algorithm, it actually takes a certain amount of time to run. So this generic like, oh, it takes n log n, like n log n times some constant factor gives you the actual thing. To make an analogy, if I like, let's say I was trying to find a an entry in a dictionary in a printed dictionary. The algorithm is like, so like one algorithm would be to kind of go to the middle page, see if the word is it before or after, and then kind of do like a binary, like a recursive decomposition. One algorithm would just be to look at the first page, see if it's there, keep flipping. That's kind of the algorithm, the running time. The constant factors on an algorithm are essentially like how fast can I flip the pages. So at the end of the day, both of them matter. Systems programming is uh, for me, I define it as programming in a world where the constant factors do matter. So like if you're trying to like get the most performance out of something, if you're trying to make sure that it can handle the biggest videos or the stream audio in the most clear fashion or something like that, when you really care about the fine details, um, those are the types of things that I've loved working on. And if you go back to the original computer that I worked on, systems programming is often described as being kind of like low level or close to the hardware. When I started programming, that's all there was. There was no Windows. There was like if you wanted to use the mouse, you had to like add code into your program to like read the mouse location and draw it on the screen or something. It wasn't something that existed outside as part of the operating system. Uh, and then layers and layers and layers of abstractions and power have been added since then. I mean that like you no longer when you're writing a program, you don't have to have a mouse draw loop in your program anymore, which is a great thing. But in some sense, I've kind of always stayed a little bit connected to the low level hardware stuff. Like I try to make it so that I'm never afraid to like open up and figure out how something works on the inside. If there's no black boxes, every black box can be opened. There's some reason why the computer does this faster than that. There's some reason why the operating system can implement this or some technique that it uses, and you can always go look, especially with open source. Like Linux is actually a pretty readable source code, surprisingly. You can actually go in there and figure things out. So systems programming is, so I want to give a specific example from my career of how a systems programming project that I did that was successful. So I spent about 10 years working at Facebook. I left right before it became Meta. So I was there kind of I started out when our biggest problem was Justin Bieber posting photos and then everybody trying to like it simultaneously. And then as it became more and more complicated in its relationship to society, fortunately I got to miss the last part of that. But there's one of the fundamental data types that's widely used in programs is called a hash table. So this is if you have say a string and you want to find records associated with the string. Rather than like in an array, you're essentially indexing by numbers. In a hash table, you can index by any type you want. And it's actually still fast. But there's a bunch of trade-offs. And there were actually a bunch of different implementations that we used internally, and none of them, they all had different trade-offs, and none of them were actually as good. So I realized that there had been a change in the state of the hardware that was available. So as part of better supporting video and audio, the CPUs, like the Intel CPUs, had added a bunch of vector instructions. The streaming was started out with MMX, which was multimedia extensions, and then it was SSE, the streaming something extensions. Anyway, so SIMD basically means that you can perform a computation instead of only on a single value at a time, you perform it on say 8 at a time or 16 at a time. So I figured out a way. So in a hash table, you're basically you kind of the hash gets you close, and then you have to search for the thing you're looking for near or kind of in some sort of a sequence from where the hash gets you in the table. So usually you end up looking one at a time, and you often find it in the second or maybe the third spot instead of the first spot, which means you have to kind of make decisions, and making decisions is hard for a CPU because it likes to predict what's going to happen, and if that prediction ever fails, then it has to kind of back up and start over. So I figured out a way using these newer instructions to check 14 slots at once. So basically, it was a 16 byte vector, and I needed two for something else. So I called it F14 because it checks 14 slots at once, which means that you almost always find it on the first try. So you end up with a by taking advantage of these new instructions, I was able to build a new hash table that was faster than all the ones that were already there. And not importantly, not only was it faster, it was not only faster when it was faster, it was also kind of never worse. So often when you have a trade-off, people are like, oh, let's build the fastest car, but then you end up with like a drag car that can't go around the corner, or you build a car that's really good at off-roading, and then if you try to drive it on the road, it's not that good. This was a situation where we were able to make something that was kind of like it was like a single, imagine a single car that's like simultaneously a better drag strip racer and also better off-road and also better on a road course or something like that. It just was like it wasn't always first, but it would always come in at least second or third, and it often would blow everybody else away. So we just switched over everything to it. And this actually ended up saving a lot of money for it was like a measurable efficiency win across the entire fleet. It was a little bit unusual because this was actually a side project for me, and all of the money that got saved wasn't even in my organization, so it kind of wasn't really part of my day job. But um, one of the things about hopefully you get a chance to work at companies where they kind of don't let the like if you do something that benefits the company, then you'll be rewarded, even if it doesn't necessarily benefit your immediate manager. So Facebook was that way at the time. One of the cool things about this was that I got a chance to open source it, and I also got a chance to like write a blog post about it and stuff. So if you ever get a chance to, one of the challenges of a computer science career is that often the work you do is kind of buried inside and hidden. Like maybe it turns into like a line item on your resume or something, but you can't really talk about it to the world. If you get a chance to open source something or write a blog post or something like that, it's actually a pretty strong way to help build your career in the long term. So now, even though I'm no longer there, like internally, people knew that I wrote F14, but now F14 is open source, and so people know about it externally as well. It's kind of it's part of my reputation. I'm going to talk a little bit more about imposter syndrome later, but when we evaluate ourselves and we look at other people, we're essentially comparing our own, like everything that we do to other people's successes. So people are like, oh yeah, you did F14. It's amazing. Like I could never have built something like that. F14 was actually my 10th try. Like I had the feeling that there should be something possible, but I tried a whole bunch of things that didn't work. And this one was one that finally did. But then even when it did, like actually telling people that it was better and kind of committing to that was a pretty stressful thing because it could have been that they deployed it even though in my benchmarks it was faster, it actually made things slower in real life. So it kind of I had to kind of like psych myself up to do that. I had a lot of trepidation about it. The gamble paid off, but it's possible that it didn't. I think the reason why systems programming has survived and actually kind of why software engine like it kind of shapes the entire software engineering industry is a thing called Jevons paradox. So Jevons was a guy, an economist, and basically what he realized was that so you would think, for example, that if you make computers faster, then that means that you don't need as many computers because the computers can, they can, you don't need as many computers to do all the stuff you were doing yesterday. But what actually ends up happening is that more things become financially viable to do with computers, and therefore you actually need more computers instead of less. So if decreasing the cost increases the demand by more than how much you've decreased the cost, then the total consumption actually goes up instead of down. The same thing with performance critical programming. So the computers today are 10,000 times faster. Well, actually, I mean, that's just my phone. Like if you go to a data center, it's way more than that. The computer that I started with, but that doesn't mean that optimizing programs and making them faster is less important now. It's actually more important because the computers now like are fast enough that we can tackle so many problems that we build data centers full of these computers. And so making those data centers faster is actually much more impactful than just speeding up my fractal rendering when I was sitting in an office by myself. I think this affects a lot of computer science jobs, not just the low level ones, like even the high level stuff. Like if you make it easier to write programs, then people will write more programs, and that means you need more programmers instead of less, which is kind of counterintuitive. I guess that's why it's called a paradox. So I think one of the big questions here, and you'd think that I would know the answer because I work at OpenAI, but I'm not. I think everybody is not quite sure what the future holds. AI is kind of on the cusp of being able to write software itself. Not clear to me how it's going to change the act of computer programming or the act of being a software engineer. Maybe this will just accelerate maybe this will just be a tool that makes it so that we can program faster ourselves. but we're still kind of in charge of the mental model and everything. Maybe it means that we can kind of we basically become program managers and like imagine that everybody had like a bunch of interns that followed them around that would just do tasks for them. Maybe they don't quite get it right, but like they're pretty good. So you become kind of like a manager, even though you don't have any reports. Maybe it's they're more like collaborators. I really don't know. I will point out though that every every step along the path for the last 30-ish, 35-ish years that I've been programming, every time it got easier to write software, more software got written instead of less. So I think AI will probably expand the amount of code that gets written, which presumably will expand the amount of value that's created, and then hopefully that won't all be captured by just a couple companies. In the bio that I was introduced with, I said I had a very discontiguous education. So I want to tell you a little bit more about the path that I took. This is partly to point out why I made the transitions. It's also partly to like if you ever feel like you're behind or it's like a race and you like other people are ahead of you or something like that, like do not worry. Okay, so when I was in high school, I competed in some math contests. I was not like the best in the best in most of them, but I was good enough that I kind of like participated in the math contest training like club that we had in nearby. And I got hooked up with a professor at UNC Charlotte, and he arranged for me to be able to go and take some college classes while I was at high school because I grew up in rural North Carolina, so they didn't really have any. I kind of ran out of math and computer science classes around the ninth grade, so I was able to supplement that by driving to UNC Charlotte to take those classes. Although that did mean that I was driving 400 miles a week for my junior and senior years, but it was an incredible opportunity. He also his daughter went to RSI the year before me, and so he, I guess, submitted my name. I didn't even know about RSI. I wouldn't have known to apply. And so he was kind of responsible for me being able to go to RSI, which allowed me to. There's no chance that I would have been able to do a PhD later if I had not done that. While I was at RSI, I was able to work on a research paper that was later published, which was so. If you do want to if you do want to go to a PhD program, it's incredibly valuable to have your name as an author on a paper. Easiest to do that while you're at undergrad, if you can like find a research group that is willing to essentially trade work for authorship. And it's okay to be upfront about that. You can basically be like I would like to help you out, but I need to be an author. Like that's an okay conversation to have. You don't need to feel like that's an improper thing to ask for. Okay, so I mentioned that I was treating everything kind of like a contest or speed run or something like that. So because I had some classes from UNC Charlotte that I could transfer in, I figured out a way to, at least on paper, a way to get a triple major at Duke in 3 years. So I was going to like speed run and somehow, I don't know, prove that I was smarter than everybody else or something. So I got about halfway through that and burned out and ended up taking a leave of absence as a way of. I mean, I basically I kind of got depressed and stopped going to class and for a few weeks and pulled myself out of it, went and talked to the dean, and then went around to all the professors and worked out a plan for how I could kind of not flunk out. But that plan involved me working incredibly hard for the last 6 weeks. And the only like the idea of like, okay, I can do this and then I can take a break for a while. Like I was able to kind of clear that hurdle. I don't think I would have been able to clear the hurdle of doing that and then coming back immediately. So I went and I worked for a year at a local internet access provider in North Carolina. So this was like this was when the World Wide Web was just starting to be a thing. People were still connecting with dial-up modems, so we actually had rooms full of modems and servers and stuff like that. That's where I learned Unix. It wasn't Linux, but it's a variant of Unix, which those skills turned out to be incredibly useful later. So this idea that when you work somewhere, even if it's not necessarily great for like long-term financial security or whatever, you taking something with you when you leave, like taking like bringing lessons with you or skills with you, like that's been a recurring theme. So that internet access provider, it got bought out by somebody else, and I went back to school. I did one more semester, and I had a group of friends that I had made because we were competing in computer programming contests. I mentioned that I was like middling at math contests. I did quite well at computer contests. So I competed in the IOI, the International Olympiad of Informatics, and got a gold medal. And so I had two other friends that I had competed in the ACM programming contest with, and they were graduating, and so they wanted me to come with them to write trading algorithms for a rich guy in Bermuda. So I did. And none of us really asked where he got his money or whether he was a good person to work for. So like one of the lessons there is that you should choose who you work for. People that are nice to you but not nice to other people, or not necessarily like, it's probably best to avoid them. Anyway, but I learned a lot, and I got to live for a year in Bermuda. Bermuda is an amazing place to visit. It can be kind of a lonely place to be a young person. There's no college there, so there's kind of like a demographic black hole around the people that are that age that are not there on a cruise ship. Okay, so then I went a couple of years of that. I went back to Duke, finally finished up. Third time around was actually kind of when I really hit my stride as like discovering my own identity and like finding my group, my social, like my long-term social friends. That's also where I met my wife. And when I was done with that, then I formed another startup with the same group of friends, actually, the same people that I had been with in Bermuda. So this time we stayed in North Carolina, and I worked in what now would be considered, I mean, at the time it was considered high frequency finance, but it's not. And I worked there for quite a while. Again, like not startup, not anything that not anything that we got like startup wealthy on or anything like that. But I gathered a lot of experience. And then I went back and got my PhD. So when I went back to get my PhD, I was about 32, which is unusual, I guess. Like by the time I was done, there were quite a few tenured professors that were younger than me. Like if I went and got coffee at the coffee shop, they would call me professor instead of sir, uh, whatever. But my wife and I both decided to go back and do it at the same time. We decided we wanted to get a PhD before we had kids, and doing that as a group thing, so both of us could empathize with each other, I think actually worked out really well. After my PhD, I instead of going to do another startup, well, actually, technically, Facebook might have been considered a startup when I went there. They still fit in one building. It was like 700 people, but it was not really not the same kind of thing. I did something that was the first time I really kind of worked in Silicon Valley. And so I spent about 10 years at Facebook as Facebook scaled. And then I left to a startup called Rockset. I'll explain a little bit more about why I left in a later slide. And then 9 months ago, Rockset got acquired by OpenAI. So I now work at OpenAI. There's a couple of things I wanted to say. These are things that kind of would have changed my career path and perhaps even my life if I had known them sooner. The first one I want to talk about is actually not a computer science specific thing. This is just something that, I mean, I think this is probably more common in computer science or engineering fields, but this actually really had a very, like an incredibly large positive impact on my life when I learned it. So somebody told me that I was an introvert, and they told me what an introvert is. So the way they explained it was that introversion is about energy flow. So if I am around people, then I lose energy. And if I am by myself or kind of in an environment where the rules are extremely clear, like I don't really have to think about whether or not I'm like how I'm interacting with other people, um, then I gain energy. And so if my battery runs down, then I'm kind of grumpy and ornery and unhappy. So before that, I just felt like I was kind of this inconsistent person, and I wasn't really sure if I liked being around people, and I felt like I didn't have good social skills because sometimes I like kind of freaked out or whatever. And after that, I realized that all I had to do was kind of manage my energy levels, and I could actually just explain things to people. I could be like, you know what, I'm feeling like I need to spend some time by myself tonight. I don't want to hang out with you. It's not because I don't like you. This improved my life a lot. Okay. I mentioned that I went back to get a PhD at age 32. So there's kind of an obvious question here, which is why didn't I do it immediately or immediately after I finished my third attempt at undergrad? I think the biggest reason is because I didn't really have any idea what a PhD was. So like I knew that like in an undergrad, you have breadth requirements, so you study lots of different things, and then you also you major. So originally I was majoring in EE, CS, and math. I dropped so that I was just EE and CS. I took a bunch of computer science classes, but I was kind of like, yeah, like I know a bunch of algorithms. Like, what do you need besides like sorted like trees and sorting and hash tables and linked lists and stuff like that? Like a master's is my mental model for a master's was just more depth. Like, okay, now you learn like more sophisticated algorithms and stuff like that. And then I guess I figured a PhD was more like a super master's or something. It was just like you would be like spending your time like debating the like super detailed corner cases of algorithms that didn't really matter in the real world. Like it seemed like it wasn't connected to anything that really mattered. This is not the way it is. What it actually is that so my idea that masters is kind of an extension of like is more depth in what you're doing, I think is generally correct. I think I underestimated how much stuff I didn't know, which is, I guess that's fairly common when you're young. But a PhD is much more than that, right? In an undergrad and in a master's, you essentially are asked to you're learning things that people already know. You're asked questions that people know the answers to. The questions get harder and kind of fresher as you get more and more into it. But a PhD is something entirely different. In a PhD, you actually have to pick your own questions. You have to find a question that uh, is not yet answered, but it is answerable. And then you have to answer it, and then you have to convince people that your answer is correct. So there's a whole bunch of things there. You need to be able to form an argument like some sort of an evaluation. Like you basically need to be able to come up with a like how will we tell whether or not our answer is correct? How will we tell whether or not our system works well? And you have to be able to convince people of it. So this actually involves kind of writing and persuasion and presentation and stuff like that. Um, and it's actually a really big step when you move. Like the problem with picking your own questions is because you might actually pick a question that is unanswerable. And then if you spent your entire life being like able to answer questions, and then now you have a question where you can't make any progress for a long time, it can be kind of demoralizing. Or you can pick a question that is too easy, and then you spend some time on it, and it's a bit of wasted work. But and you have to be able. I guess I probably should have added it to the slide, but you also have to be able to connect your answer to everything else. So um, I sometimes describe a PhD as walking with baby steps, where you have to do kind of heel to toe walking. Like if in industry, if somebody needs a thing solved and you write some code and it seems to work, they don't really care exactly why you did it the way you did. They don't like nobody's going to ask for an experiment to prove that it works because it works, or an experiment to prove understand exactly why it works or something. Whereas in research, you kind of have to, if you're going to publish a paper about something, if you say, well, we did blah, you have to kind of explain why. And that can either be an experiment or an argument or a citation or something like that. But you have to kind of connect your steps one to the next in order to be able to justify how you ended up where you ended up. Um, Okay, so the epiphany that I had when I was 31, and I'd already been programming as a professional for, I don't know, like 8 or 9 years cumulative, um, was that all this like algorithms, confidence factors, this was not the hard part. The hard part is actually just fitting things in people's brains. So cognitive load, like the ability for somebody to understand how the program works in order to be able to debug it or change it uh, uh, or or build it in the first place. This is actually the real limit always. The fundamental tool that we have in computer science and in a lot of different disciplines for dealing with this is abstraction. So, for example, instead of like go back to the hash table implements the abstraction of a dictionary or a like kind of an array where you can index into the array by a string instead of by a sequential set of integers. You can kind of reason about the hash table at that level without thinking about the internals. That's why I was able to swap out F14 for a bunch of other hash tables that weren't used. We all used the same abstraction. I had a better inside. So this abstraction boundary effectively gave us a point at which everybody else could worry about their problem. I could worry about the F14 problem, and we could both apply a lot of brain power to our side of the boundary. And as a result, we were able to build a system where nobody really could hold the whole thing in their head at once. Choosing these abstraction boundaries and choosing good abstractions, it expands the scope of what's possible, like just as much as if I came up with a better algorithm for doing something. It opens up the space of possibilities that can actually be built. And abstractions are like they kind of build on top of each other, and it's this is still a field that's completely wide open for mere mortals. Like you don't have to be somebody that can like create a breakthrough algorithm in order to be able to uh, take a problem space and come up with a better way of thinking about it. So this is simultaneously possible, and it's also interesting, and it directly applies and is useful, and that actually got me a lot. That got me excited about doing it. Before that, I didn't really see the value, and afterwards, I realized that it actually it did potentially it did actually potentially contribute to what humanity could accomplish. So doing a PhD after you've been a professional programmer is kind of a blessing and a curse. Like so I could like program rings around all the people that uh, like for a lot of people that are doing a PhD, like the system they're building is kind of their maybe their first or second really big project. Um, there's kind of a problem with the way computer science is taught, where like there's a lot of focus on writing programs, but there's not a lot of focus on revising programs. But in the real world, you actually spend a lot of time revising and fixing and debugging and modifying and stuff like that. So it's kind of an under-taught skill that you needed a lot during a PhD. So being able to like use version control and write unit tests and stuff like that, it made the hard skills part go quite well. There's another advantage here, which is a lot of a lot of researchers are kind of like they have something that they like kind of a technique that they're evaluating or whatever. They're essentially they have a problem. I mean, a solution in search of a problem. If you've been working and built real systems, you have tons of problems from your past, and so finding being able to like explain to people why a particular technique is useful or a particular system is impactful is much easier if you've actually worked in the real world. It is a pretty big pay cut. PhDs pay, but they don't pay that well. The especially like if you're so I went to Stanford, which and I lived in San Francisco, which is a relatively expensive city. And the workload is, I mean, you get a lot of flexibility in your workload, but it also is sometimes pretty high. My wife and I had a metric for how we thought the PhD was programming. I mean, sorry, how our PhD programs were progressing. So the metric was how many days had it been since the last time we looked on a job board for a job that did not require a PhD. And for neither of us did that number ever go above 30. So that means that like I mean a PhD process is can be emotionally grueling. Like there was never a period of a month where at least one point in that month I didn't think about like what would it look like if I didn't finish. Um, but I am glad that I finished. One of the things that I love about this model of thinking about computer science as or like advancement as abstraction, and also one of the reasons why I love computer science in general is that it means that this is not a zero-sum game. This is especially a problem in our world right now. But like there are people that basically feel like the only way they can win is if somebody else loses. And there's environments in which that's true. Like if you're wrestling, the only way you can win is if you pin the other person. There's environments and contexts where you succeeding actually makes it easier for other people to succeed. I've done a lot of rock climbing. The part of the reason that I like rock climbing is that it's simultaneously you're challenging yourself, but it's also not. You can devote that competitive energy not against other people. You can actually be very cooperative with them. Like everybody makes it to the top, everybody succeeds, and I really like that. My wife is in biotech, and there they have a bit of a problem where you spend a bunch of money to gather data, and there's only a certain amount of scientific research that's going to come out of that data. Like if you've just genotyped a bunch of stuff, you're only going to find one gene, or sorry, like you're not going to find an infinite number of genes in that data. So that structure leads to more competition and requires a little bit more kind of you have to be really upfront with like who pays for things and who's going to be able to actually publish based on the results. So one of the questions that I get asked fairly often is like, what does a PhD mean as a software engineer? Like, I could have worked at Facebook without, I mean, like famously, Mark Zuckerberg dropped out of undergrad to go start it, and he was able to do that. There's no technical requirement for even having an undergrad degree in order to be able to work on the kind of stuff that I was working on. One of the reasons to get a PhD is because it's in an area that you're passionate about. You essentially get like 4 or 5 years to just like really learn something deeply, which it's a real gift. Apart from that, once you actually are in a software engineering career using a PhD, it gives you more opportunity to work on interesting problems. So like if somebody has like a really tricky problem, a really hard problem, like they're more likely to come to you to solve it. And those are the ones that are the most fun to solve. Even when you're not writing research papers, answering like figuring out how to come up with how to answer a novel question is actually like a very reusable and portable skill. So it's like actually a really common question is like, okay, we have the system, it has a problem, we're going to try to make these changes in order to fix it. Is that actually gonna like it's easy to understand what the bad parts of the system are because they pop up they like the system crashed. We know there's a bug there or whatever. There's a like the system got overloaded. We know we need to like move this data, spread this data out or something like that. But the system probably has a bunch of good properties, and the good properties don't necessarily present them to you as well because they don't cause you to notice them. There's no log message in the error log that says, "Oh yeah, like I was able to handle this request because of this thing." You only get a message in there if the request failed. So studying the systems to understand why they work well, or like what are the good properties that you need to preserve, is a very research-like activity. You have to formulate a way to evaluate it and a way to be confident. Um, and otherwise, whenever you got to go try to change the system or make it better, you actually risk making it worse, especially for systems that are relatively mature. The PhD has given me more opportunity to publicly share my work. So, for example, I worked on a system called Tau at Facebook, and I wrote a research paper about Tau, which was published, and it's kind of given me a chance to be uh, kind of like the external expert about that system. And I've gotten to have a lot of interesting conversations with people that I've learned a lot. Because basically, when people ask you hard questions about something, that's a really good time when you learn about it. If you can think about it and figure out an answer, maybe even a year later or something, then you've learned something. So by being able to publicly talk about things, or publish research and then engage with the research community, I've learned a lot that way. A PhD, I think the research says that it doesn't actually get you more money in the long term. It is true that having a PhD gives you kind of a higher starting salary, but there's an opportunity cost for starting a few years late. So this is not the reason to do it. You should do this because it lets you, like, well, the first thing here, the opportunity to work on interesting problems, I think is the most compelling. Okay, so when I finished my PhD, I felt like I had kind of four categories of options. Academia is always a possibility. You can be a professor. I'm an introvert, so having to spend all my time interacting with students and standing in front of a class didn't seem that appealing. Um, I could have gone back to finance. Um, I'm pretty happy to not be there. Finance is there are positions in the finance world that pay quite well, but they're also like very demanding, and it has a lot more of this kind of zero sum, like zero sum nature, and it's also kind of like, immoral is not the right word, but amoral, kind of like it's morally neutral at best. The main two things that I was considering were tech, like actually like writing software that is either being kind of sold or that's powering something, or going to a research lab. And research lab was originally my main choice because I was like, oh, I really like doing research. I like writing papers and talking about them. Well, I actually don't like the process of writing. I like having written papers, maybe I'll say. But then I realized that most of the, like, essentially all of the work that was being done at research labs wasn't being done like to benefit, to add to humanity's knowledge. It was being done in order to, well, there's a small fraction that's being done to unlock potentially new markets. So, for example, Intel was trying to sell multi-core chips, so they were researching multi-core software because they found that people were having trouble using the multi-core chips. So they were trying to grow that market. But most of the research that happens in research labs is there for the purpose of patenting something in order to be able to kind of lock it up. And that didn't seem like it would be something that was super motivating for me. So I decided not to do that. If you're working in industry, there's actually a bunch of different kinds of software you might be writing. You might be actually creating the software itself that's being sold. So, for example, you might write, I don't know, like a game, and then the game gets shipped. Um, you might be writing software that runs as a service. So, for example, when we were working on at Rockset, we wrote a database, but we actually hosted the database ourselves in the Amazon cloud. So when you're running it as a service, or if you're kind of like an infrastructure service in a larger company, like happened when I was at Facebook, um, there you actually have the ability, you kind of like, you own the whole life cycle. Like if your software has a bug, you're the one that gets woken up in the middle of the night, or like when it's your turn to carry the pager. If your software works well, then you get to see the expansion. You're kind of owning and operating. And there's a pretty big distinction there between whether your software, like one distinction is whether your software is a cost center versus a profit center. So a cost center is essentially something that the company has to do, and they're trying to do it as cheaply as possible. And that's not a great place to be, because they're basically trying to get it done with as few people as possible and spending as little money as possible. So like it means you're kind of constantly being asked to do more with less, and it's kind of a stressful thing. If you're doing something that's a profit center, people are basically, they feel like if you do a better job at your job, the company will make more money. And that means that they're willing to invest in growing you and in growing your teams and growing your systems and stuff like that. And it's a much nicer place to be. Um, and you can also be in a situation where you're writing software that's critical to the company and critical to its growth and survival, but it's not actually something that somebody else could, like, it doesn't enable competitors to compete with it. So, for example, when I was working on database software at uh, At Facebook, we could talk about that publicly and publish papers about it and stuff like that. Because the reason why, like, people weren't competing with Facebook, like, it wasn't like the competitors were blocked on competing with Facebook because they didn't have a good database at the bottom. That was not a competitive advantage. It was an essential component of Facebook, but it wasn't something that they felt like they needed to keep secret. And that was a really nice place to be because it gave me the opportunity to be in this kind of like I get to talk about things space. It gave me access to kind of large scale. So when you're at a small company, it's like a startup. It's really easy to see your impact. You can completely change the course of the company by writing code and doing individual work. And you get to learn lots of stuff because there's not that many people, so somebody has to do everything. It's very fast paced. It's usually much easier to kind of make decisions about what should be done. Like if you only build one thing, then making that thing work better it's pretty clearly that's what it should be. If you work at kind of a large company that has lots of different products, then you end up with these like, well, is it more important, like if I make this thing better, then does that thing get worse? Like, decision making gets very fragmented. As you get further in your career, it's easier to stay as a coder at a smaller company rather than a larger company. At a larger company, they want you to kind of be this like meta tech lead type thing. I mean, I'm assuming you don't go into management. Large companies have a lot of advantages too. So they have interesting workloads. Like the Tau system that I talked about, when I left, it was running 4 billion queries a second. So that's four queries every nanosecond. I think now the number is up to 20 or 30. You have the opportunity to potentially learn something very deeply because even kind of small improvements to the core of these like complicated things can actually be impactful enough to justify spending a lot of effort on it. And then larger companies tend to have kind of they understand they've got better systems in place for doing mentoring and career progression and stuff like that. And they also like they pay better and they pay you immediately. Whereas like a small company, you might like there's some outside chance of making a lot of money in the long term, but in the short term, the pay's not as good. And large companies, because of their scale, often end up like they have problems that can't really be solved by any off-the-shelf software. So you actually really are doing something novel. My recommendation is if you go to a startup, make sure that whatever you're doing advances your career, even if the startup fails, because most startups fail. So make sure that you're learning something that you will be able to kind of reuse that knowledge later or stuff like that. And make sure that you are like it's okay to be optimistic, but you should be prepared for downside as well. The flip side advice, if you go to big tech, is that you need to be careful about kind of being trapped there. Like if they are happy with you being there and they want you to stay, it's very like they'll be like, okay, we're going to give you stock options, but or stock, but it's arriving over the next period of 4 years or something like that. So you keep seeing that money there, and it makes it really hard to leave, even if you want to leave, even if you're getting burned out. And so people sometimes get stuck. If they get a higher salary, they immediately spend it, and then they can no longer they lose the option of doing something else because they've kind of gotten stuck in that hedonic adaptation. I mentioned that it's hard to stay coding if you are as you progress your career in big tech. There's kind of this notion that it might be surprising, or it was surprising when I learned it. You don't necessarily get promoted because you're doing a good job. You get good performance reviews and raises and bonuses and stuff like that for doing a good job. You get promoted when you're working in a different way. So like if somebody's giving you tasks to like they're like, okay, you need to code up this thing and you code that up like super fast. Like maybe you can do it 10 times faster than anybody else. Like you're doing an amazing job at your level, but that's not actually operating at the next level. The next level is figuring out what should be coded instead of just doing the coding. And then you figuring out what should be coded like within your team, figuring out how teams should like the API boundaries between teams, figuring out what the long-term decisions are for the entire organization or even the company. These kind of like strategic, like we have these two large databases and we should replace them with a single large database because of blah or something like that. Projects that'll take years to do. Those are the kind of like that increase in the scope of what kind of decisions you're making is kind of what is attached to promotions. So it's totally fine to like like you can't stay E3 forever, but you can stay like E5 forever, these companies, where you're still like only focusing on a single team, kind of a teams level view, and you can do quite well that way. At Facebook, I essentially promoted myself out of doing a job that I liked doing. I got promoted and to the point where they didn't really want me to write code anymore, and I love writing code, so I switched to Rockset. My advice for when you're making these transitions, if possible, is to find a team of people that you love working with. So I actually knew several of the people that I went to, several of the founding engineers at Rockset when I went to join them. And so I knew that I would enjoy working with them. One of the things that I completely undervalued when I did my undergrad is how much kind of soft skills and relationships matter. So when I go back and look in retrospect, like I didn't Dr. Ryder, the person who hooked me up and eventually like helped me get into RSI, the person that I worked with at RSI, like my internship mentor, who like after I had done my research, submitted it to a journal so that it would be published. Like he didn't, that wasn't something I asked him to do. He did it on his own. Um, those were things that I didn't realize until like many years later were actually extremely helpful to me in my long-term career. So I'm not going to go through the whole list of people that have kind of helped me out in ways that I didn't necessarily even recognize at the time, or maybe it took me years to figure out how helpful or impactful it was. In all of these cases, these are people. These weren't just people that I was like friends with, or people that I mean, I was friends with a lot of them, but they were people where I had actually worked closely enough that like they could actually write a letter where they said something like, I worked closely with Nathan on blah, and in my opinion, he's in the top like 10% of all the interns that I've worked with, or something like that. The relationships you have, if you have even just like one or two where somebody actually knows you to that level, that actually can be a huge force multiplier in not only in your academic career, but also in your kind of getting into good positions later. The last thing I wanted to mention is imposter syndrome is widespread. So when I was in like late high school and early college, like from any objective measure, I had no reason to feel imposter syndrome. Like I had come in like first in the world in a programming contest, and yet I did. Like success doesn't actually like solve imposter syndrome. There's so many different metrics that we can compare ourselves by. We're like, well, maybe I'm a better programmer than that person, but like they're better than me in all these other ways. We compare like the worst part of ourselves, or like all the parts of ourselves, to just the best of everybody else that we see. I mean, you guys know about this from like people presenting their Instagram life versus their real life and stuff like that. So for me, like my fundamental fear is a fear of looking foolish. And this is kind of a double-edged sword. So um, you can actually kind of harness that type of imposter syndrome feeling as a driver to like get better. You to like be like, I want to be an expert in this thing because I don't want to like when somebody asks me a question, I want to know the answer. It can drive you to excel. But a lot of times it can also kind of stop you from trying. So like I feel like I look bad as a dancer, so I feel like I don't want to dance if I go to a wedding or something like that. But that also means that I'm not going to become a better dancer. So I think it's important to find when these types of feelings are kind of working against you, and then make sure that you can move past it. And lots of people have strategies. So the ones that I use, instead of trying to like evaluate myself against perfection, I one of the things that I do is I'm like, okay, do people like instead of like these people are going to feel like I'm not doing a perfect job, like, well, do they say that they like working with me? People say they like working with me, so it doesn't matter that I'm not as good as I feel like I could be or should be. When I find somebody that's really good at something, I try to remind myself that like they actually spent a lot of time to be good at that, and it's quite possible that I could also be good at that if I had spent as much time, but that there's an opportunity cost to that. I would have had to spend a bunch of time doing something else. I'm pretty good at origami. If I was going to be better at something else, maybe I wouldn't be as good at origami because I wouldn't have had time to devote to it. It's also important to remember that a lot of the processes of like which college you get into, like whether or not you make it past tech interviews and stuff like that. There's a lot of randomness involved. So rather than feeling like you shouldn't be somewhere, you can feel like you're fortunate to be there. And it's okay if there's somebody that's stronger that didn't get there. That's just like maybe you got lucky this time, maybe they'll get lucky next time. You can just kind of you can treat it as an advantage that rather than a disadvantage. And then finally, there's a weird effect where that I've found where it seems like when if you make a mistake and then you realize it later, pointing it out will make people be like, oh, that person makes a lot of mistakes. But pointing out your own mistakes or being like or changing your mind, saying like, oh, like, well, I thought that this was true because of blah, but then I realized that blah, like that actually makes people trust you more rather than less when they can kind of see the transparency of your process.
Thank you so much for that wonderful presentation. I think you covered a lot of real topics that our students are thinking about, especially around the soft skills that go into going into post-secondary education. So we got some questions coming in here. I'm going to start us off with the first one that came in. So this is from a parent. So my son is a high school sophomore and wants to know what are the most common careers for computer science for the future. He loves coding, but isn't sure what he's learning now is going to be relevant in 4 years.
There are a lot of like rapidly changing things. So I've had a little bit of an advantage because like I've been able to like kind of adapt to a lot of changes as they happen in real time. Like if I started programming 30 years ago, then all of the changes that happened over the last 30 years have I've had 30 years to adapt to them. It feels like the pace of change is very rapid right now, but it seems like being able to understand how like the low level details of how things actually work, that's still like a really powerful thing. Like even if even when the AIs are able to like write a bunch of glue code or something like that, like at the bottom there's still physics. There's still like bits that have to get from one place to the other. There's still limits on how fast things can go. And I think that this goes back to the value of a PhD, but being able to ask good questions is like AIs are getting to the point where they can come up with answers, but they're still pretty far from being able to like change the way that we think about things or ask questions that bring us new insights. And so I think that's something where if we focus on being able to like deeply understand things, then that will continue to be valuable.
So going forward with that vein about AI, what role do you think companies creating AI models have in ensuring their products are used for good?
I certainly think that that's something that they need to be thinking about in terms of like I think there's parts of that problem that are the responsibility of the companies, and there's parts of that problem that can really only be solved by kind of some form of collective action. Ideally, that would be government. Although the government right now seems to have other focuses. There's a big question here also between the open source models versus the kind of hosted models. Um, the open source models are much harder to like if you actually if you're running the open source model, you can kind of see what's going on inside its brain, even if you've told it. Like I saw a really interesting research where they were actually able to kind of identify which neurons were keeping the open source model from doing something that it had been trained not to do. And once you identify that particular pattern of firing neurons, you can actually run it in reverse. So they were able to take a model and essentially tell it like do the thing you're not allowed to do instead of do the thing you are allowed to do. They were able to kind of like turn up its like flip the inhibition into a exhibition is not the opposite, but something like that. I don't know. That's a big challenge.
Are there any regulations with AI that you personally think should be implemented or are looking forward to having been implemented?
I think the biggest worry for me is the kind of broad economic impact. Assume success for the first year, and then in 1 year we'll have a conversation about whether we want to go back. So you kind of like break risk up into a thing where you're basically like tolerating risk and then evaluating and trying to like collapse it and remove it. And this is a technique that I've used all through my life to get through to kind of like you essentially ignore stress and you say like, okay, this stressful moment, or this stressful thing, like I'm gonna put a thing on my calendar for when I need to think about it, and I won't worry about it until then.
It's like accepting that rest period opens you up to for more productivity because you gave yourself that grace to kind of pause and think about it and then put it
And it
on the
lets you,
shelf.
yeah, and it lets you put 100% of your conscious and subconscious energy into the activity at hand instead of into constantly worrying. Like,
Well, so I'm gonna do one more question. We still have a handful of questions in the chat, so I think after the presentation, I'll email those to you, and you can send me those answers back for our
sure.
audience. So sorry to you all that I did not get to those questions, but we just had so many great ones, and I just had to pick and choose. Final question: what are some of the most exciting things you have recently worked at or on at OpenAI?
So despite the fact that I work at an AI company, I don't actually work on the AI itself. The AIs they get a lot of stuff done with OpenAI calls them tools. Essentially like the models themselves, you can imagine like an extremely intelligent, well-educated person sitting on top of a mountain. They don't actually like you can go and you can ask them a question, and if they know it already, they'll give you the answer. But this like oracle on top of the mountain that doesn't know anything since whenever the training model happened, it could say, you know what, I don't know the answer. I don't know what the weather is like today. But if you ran this query and you gave me back the answer, then I could tell you what the weather was like in or if you ran this web search query and gathered a bunch of documents, then I could answer this question. It also, you can imagine it doing the same thing over a bunch of, like I've uploaded a bunch of documents, or like maybe it has access to being able to search over all of the Slack of a company or something like that. So basically the AIs, they figure out the steps that are needed in order to solve something rather than just knowing the answer immediately. And then they use tools to actually go out and find that data. So I've gotten to work on one of the systems that is used that's underneath that. And so essentially, when you ask a question to the AI, it doesn't know the answer, but it knows how to query the system that we do in order to get a bunch of possible answers, and then it quickly studies them and learns the subject and gives you back a kind of a tailored answer, even on information that was only uploaded like a couple seconds earlier. And that experience is like it's just magic when it works. Like you basically just you ask it a question, it'll be like, oh yeah, like so and so was talking about it yesterday in Slack. Here's a link, and it's kind of like I did an internship at Google a long time ago, and the internal wiki search at Google was surprisingly bad. It was kind of a meme because like Google's PageRank algorithm doesn't really work on structured documents where they don't. There's not a lot of popularity. Like popularity doesn't imply value. Um, and this is the first time I've ever worked at a company where you can ask a generic question and and find the documentation, even if you didn't know the proper term and stuff like that. It's very exciting to see it work.
Very cool. Thank you so much for sharing with us. Thank you to our audience for joining us. I'd like to thank all of our sponsors that make this programming cost-free to you all, including the Claude Moore Charitable Foundation. Without our sponsors, we would not be here. Again, thank you for joining us, taking the time. I hope you all have had great spring breaks if you're on spring break, and I hope you rested well if you've already been there. Please, please, please take the post-webinar survey, log what you think about our programming, give us your feedback, and also it logs your attendance. So I know who's our repeat customer, who's been coming through and getting the programming that we so value here. Again, thank you.